have Matthew Klawan, who will be giving us a hands-on tutorial on our first neural networks, getting them set up, and show us a little demo.
Yeah,
Take it away, Matt.
Sounds good. So today we're going to jump right into working on some real neural networks on our machines. If you got the email that was sent out about the seminar, it had some links for some installation. Here's an overview of what we're going to do. We're going to review deep learning. I don't know if any of you came to the last seminar, but Kara gave a really good talk about sort of the theory behind deep learning. And this is going to recap some of that and then dive into some implementation and practical things that you have to consider. So we'll get started, and then we are going to create, train, and evaluate a deep neural network for the task of recognizing handwritten digits. And then we can discuss some more applications that these deep networks can be used for. And then at the end of the presentation, there is a bunch of slides for really nice references and tutorials and that sort of thing that once we put the slides up online, you will be able to look at and go back to if you want to review them. So just to review, deep learning models are models which use many layers of data processing to achieve your end goal. So as opposed to conventional machine learning where you have your data goes through maybe one or two steps of some kind of learning algorithm, deep learning has many steps. And this doesn't just apply to neural networks, although that's traditionally what deep learning refers to. It applies to any combination of models which are used in sequence. So for example, you might have a neural network which you use to do some sort of feature extraction for a task, and then you feed the features that are extracted by the neural network into a support vector machine. And that is still considered altogether a deep model because you are using many layers of data processing. As I touched on in that example, intermediate layers of the processing often correspond to learning some sort of feature from your data or some group of features from your data. So a good example is in image recognition, when we use deep learning models to, say, pick out the face in an image. One of the things that is done in a traditional neural network that's applied to that kind of task is intermediate layers correspond to learning different facial features and trying to detect whether or not they exist in an image. So for example, you might have one layer which corresponds to trying to detect if there is a nose present in the image, one corresponding to detecting eyes, that sort of thing. And currently this sort of deep learning approach is achieving state-of-the-art performance in a number of fields, not just image processing, but natural language processing, signal processing, et cetera. And the sort of explosion of deep learning in the recent decade, I guess, the most recent decade is a combination of advances in training approaches, so how we are training these models and how we're running them, and then also the hardware has really gotten to the point where training these deep networks is becoming practical. So getting started, by a show of hands, just so I know what the audience is doing, how many people were able to install any of the packages that were included in that email that got sent out? It's fine if nobody did. That's a sort of, unfortunately, I don't think you can sort of import something into Python, so it might not work. But it's not a big deal. You can just follow along in the slides, and I'll be going through. And then I think we are able to post these slides later on so that you can download some of these packages and try some of this stuff out for yourself. So yeah, in order to do this, there's a number of dependencies, but nobody has any of these installed, so I probably won't bother explaining too much. The biggest thing is that we're going to be using Keras, which is a Python deep learning library. Keras is built upon Theano, which is a more general tensor manipulation library for Python. And then Theano is built on both NumPy and SciPy, which are very generic mathematical and scientific operations that are provided for the Python programming language. And it's worth noting that a lot of the critical sections of these codes are written in something faster than Python, like C or Fortran. So speed is, while it's not going to be as fast as an implementation that you might have in pure C or something like that, the drop-off isn't quite as severe as it would be if it was pure Python versus pure C. So that's sort of a nice thing about these libraries. And also, as we'll see, Keras is very high level and pretty easy to get started with, which is why I chose it for this tutorial. So diving right into some deep neural networks. As I said, a deep learning model is multiple layers of data processing. So a deep neural network is something that has more than one, a neural network that has more than one hidden layer. That's sort of the go-to definition. Traditionally, when people refer to deep networks, though, they're probably not going to talk about a neural network that has just 2 layers. We're talking tens to dozens to even 100 or more layers in a neural network. And those get really complicated. They can be trained using backpropagation, and they're really good for picking out features from sort of a raw image. So if you have a task where it's not necessarily intuitive to pick out a feature set that you think is going to perform well in a machine learning task, like classification, for example, deep networks are often turned to learn those features for you automatically and try to get a good performance on your task based on the features that it learns. And often problems are more naturally modeled in deep networks than they are with shallow networks. So in theory, you can have a 3-layer deep network that can compute within reason just about any function that you throw at it. The problem is that it's really hard to find the right combination of parameters and network structure that's only 3 layers deep to get good performance on that task. Whereas with a deep network, we can draw some inspiration from biology and our own common sense, I suppose, and achieve some, without racking our brains constantly, achieve some good performance with more generic network structures. So yeah, and they're very powerful. So that's evidenced by the fact that they're doing very well with just about every machine learning task these days. So some of the challenges that have traditionally prohibited deep neural networks is this thing called the vanishing gradient. So I don't know if anybody here is familiar with backpropagation, but it's essentially the algorithm by which neural networks are trained. It involves calculating the error at output and then taking that error and backpropagating through the network, meaning at each layer in the network, you're going to learn from the error of the layer ahead of it and adjust the weights between those layers accordingly. And one of the problems with that is if you have a really deep network, in the past, what happened was your error tended to either go to 0 before it reached all the way back into the network or blow up to the point that it wasn't useful anymore. So that's what's meant by the vanishing, and then the vanishing gradient, and then the opposite of that would be the exploding gradient, where the gradient is getting so large that you're not going to be able to adjust the weights in the network appropriately. The power of deep neural networks is also accompanied by they're prone to overtraining, which means that they overfit your training data, and you might get really good in-sample error. And then when you try to generalize it to data that you've never seen before, your performance goes way down. And that's a problem for all machine learning models, but especially ones as powerful as deep neural networks. And also they still are very slow to train relative to other models. But these things have been sort of addressed over the past decade, really starting in 2006. One of the things done to address the vanishing gradient problem is clever weight initializations. Basically, some people propose that you start out with your weights in the network initialized a specific way based on the network structure. And this helps to avoid the gradient exploding or vanishing during training. Another technique to limit the overtraining is unsupervised pre-training. And basically, unsupervised pre-training of each individual layer of the network can trap the learning algorithm in a local basin of attraction is what the paper calls it, where it's more likely to learn a good local minimum for its error function that then limits, how much different it can be, the error can be during training than it is outside of training. Also, these things called dropout layers, which prevent different parts of the neural network from learning the same thing, which is something you don't want because in the best case, you have some redundancy built into your network and you're not getting as much power out of it as you could. And in the worst case, what you're going to do is you're going to give too much emphasis to, say, one feature that you've learned from the neural network than you want. So then the last thing that most people are probably familiar with is that GPU advances over the past 10 years have been really great for not only playing video games on our laptops, but also for training neural networks. This the advancement of the gaming industry has actually pushed the GPU companies to develop faster and better machines, which are then applied to science. So we're going to jump right into creating one of these deep neural networks in Keras now. And we have an example here that's from a larger tutorial about deep learning in general, and it's really good. I recommend it on GitHub. So this one is the specific example of a deep network in Keras is going to work on classifying these handwritten digits from the MNIST data set. So basically you have 60,000 training examples of people handwriting the number 0 through the number 9. And you try to pick out, what's a 0, what's a 9, what's a 7, so on. So the imports here, the only things that you need to take note of are these Keras imports. So we have a sequential model, which I'll get to in a second, what that means, and then also different kinds of layers. So layer type in a neural network corresponds to, if I go back to an image that I have back here, each layer has a specific type, and that corresponds to what function it computes over its input data. And then we have those dropout layers, as I mentioned, which are used for preventing overtraining in the network, basically stopping different parts of the network from learning the same thing. And then an optimizer, which is our learning algorithm, that's going to tell the network how to change the weights based on the error function that we've defined for the network and how far off it is at the beginning. So this is what creating a neural network in Keras looks like. It's pretty straightforward. You define a sequential model, which basically means a model in which the layers are specified one after another. And then you just add the different types of models that you want at intermediary, or the different types of layers that you want at intermediary steps, with the first number in each of these constructors corresponding to how many hidden units you want in that specific layer. So for example, in the first layer, we have a dense layer, which totals 500 hidden units, 500 units, and has an input dimension of 784. The input dimension just means that's the size of the vector that we're going to pass in as training data to this network. A dense layer rather is simply a feed-forward, fully connected layer, which has each node in its layer connected to each node in the next layer. And then after we add these dense layers, you'll notice that we add an activation layer. The activation function is basically a transformation that's applied to the function that the units compute. So in this one, we have an activation function, which is the rectified linear unit. Basically, a graph of a rectified linear unit goes from 0 to 1, it's a line increasing, and from 0 back to negative infinity, it's just a line at 0. So one thing to note is if you're familiar with neural networks, that might look like a funny way to represent it because the activation functions are typically connected to the layers directly. In Keras, it's possible to specify that a certain layer has an activation function and you don't have to add this extra activation function layer. And then at the bottom here, we have something defining our optimizer, and then we compile the model. So that's a pretty general pattern. You add layers to the model, you specify your learning algorithm, and then you compile. So I described the dense dropout and activation functions already, and there are many more layers which are implemented in Keras that you can take a look at this link. And one thing about Keras here, it's a really nice and modular design. It's very easy to come up with the structure of the network that you want pretty quickly. So something to take into consideration when you're constructing your network is your optimizer choice. So RMS prop is the one that's used here, which is basically a variation on gradient descent, on batch gradient descent. And ironically, this is actually an unpublished optimizer. So the people who reference this optimizer typically refer to slides from a famous lecture from a professor at the University of Montreal, I think. And it's pretty commonly used. I guess that gives you an idea of how fast the field is changing, just because people are implementing things that haven't even been verified by peer-reviewed journals. And choosing an optimizer is non-trivial, and it's important too, because that's essentially what's doing the learning in your network, right? New algorithms are being written almost constantly. So that actually feeds into a larger theme of hyperparameter selection in general. It's probably one of the most challenging parts of creating a neural network is choosing the hyperparameters correctly. So the optimization for traditional hyperparameters in machine learning models tends to involve techniques like cross-validation, grid search, that sort of thing, where you basically try a bunch of different hyperparameters and see which ones do the best on a validation set that you've defined in your network. The problem with doing that with neural networks is there are a lot of hyperparameters that go into creating a neural network. And so a search without some outside idea of what's reasonable, a search over the different values that you could choose for these hyperparameters would be too time consuming to be practical. There's actually a whole subfield of computer science dedicated just to hyperparameter selection called Bayesian hyperparameter optimization, which basically tries to balance the fact that you have to look for a lot of different hyperparameters with the fact that you don't have that much compute ability. So in many cases, this approach is so new that it doesn't do better than random search. And in fact, random search is one of the best ways to look for hyperparameters in a neural network if you're going to try something different than selecting them by hand. So as an example of some hyperparameters that you might have to define in a neural network, optimizer specific parameters. So I don't know if any of you have taken machine learning, but if you're doing some kind of gradient descent on a function, you have to typically specify a learning rate and a momentum, which tells the optimizer how fast or how much weight it should give to each correction that it wants to apply to the network. And there's sort of a physical analogy of gradient descent being like a ball rolling down a hill, except that we're trying to get to the bottom of the hill without overshooting it or anything like that. So that's where the physical analogies of momentum come from.
So is that like how much it tries to change each direction?
Yes, yeah, basically. So that would be a learning rate. And then the momentum sort of specifies, wow, if every change that I've made so far has done really well and I've improved performance, then I'm going to pick up my momentum, quote unquote, and change even more because it looks like I'm really progressing down a hill to a local minimum. Some other weight or some other hyperparameters include the weight initializations. So all those connections between each layer in the network are weights, and you have to initialize those weights with some value. That's what's going to change over time in the network. So if you pick a good initialization to start with, you have a better chance of reaching a good performance at the end. Regularizations are just things that you apply to a network to try to avoid overfitting. Epochs is how many times you train the network over your training data. And then there are some pseudo hyperparameters, I'm calling them. So they could be considered hyperparameters depending on who you ask. And that includes the actual choice of the optimizer that you're making, the activation functions that you're using at each layer, how many units you have in each layer, and layer type. And all of those things affect the performance of your network. So jumping into how we would train the network once we've selected these hyperparameters, and I have references at the end of the slide that sort of show best practices for selecting these sort of things, just so you're not left totally in the dark. And when we're training our network, we in Keras, we just use this model.fit command with our training data. And what's happening here is that the Keras code, because Keras is a high-level library built on top of Theano, this Keras code is being compiled to Theano variables. So basically, Keras provides a high-level abstraction that tells the Theano variables, which are tensors, how they relate to one another. And then Theano does the work of invoking the GPU or CPU for learning. So some things to note here. The number of epochs is basically specifying how many times you're going to go forward and backward on every training example in your network or in your data set. So as you can imagine, the more epochs you specify, the better a chance that your model has to converge to a good result. But also for every epoch you're specifying that you want to run, that's another, in the MNIST case, 60,000 passes forward and back that you have to compute. So it's expensive and sometimes not worth it to add more epochs just for the sake of getting better performance, because you're going to experience diminishing returns on your network eventually. Batches specify how many groups of training examples are fed, or the size of a group of training examples that are fed through the network before the weights are updated. So a batch size of 1 means that you're going to update the network after every training example you feed through. Sometimes you might not want to do that. One of the most obvious cases where you wouldn't necessarily want to do that is if you're doing some kind of natural language processing. Let's say you have a sentence and you're trying to predict the last word in the sentence. In your training data, you don't want to update your network by every word. You want to update it for every sentence, right? So you're going to feed in all of the words in the sentence first before updating the error on the last word. And the reason that you would feed some of the training data through in the first place is that feeding the training data forward might alter the state of your network depending on how you have it defined. So if you have a network which can quote unquote remember the last word that it saw, then every time you feed it a new word, it's going to remember the previous one. And that might help you predict what the last word is going to be. So that's an example of where batch training really comes in handy. And then also something to note here is that validation data is specified. Validation data is really critical if you want to do any kind of hyperparameter optimization. And that's true for all machine learning models, not just deep networks. And that's because were you to train on training data and use the training data to validate your model as well, and pick from essentially what is a group of different models which have different hyperparameters, what happens is you are losing some of your ability to generalize from your in-sample error to your out-of-sample error. So validation set sort of keeps your models honest and still lets you fiddle around with the different hyperparameters that you might choose in the model. And then, so something to note is that Keras can be trained on both a GPU and a CPU. So GPUs are traditionally faster than CPUs for neural network training, and that's because of their origin as sort of the main compute device of games. Games require a lot of matrix operations, and coincidentally, that's also what deep learning requires, is lots of matrix operations. So it's sort of a good match, and that's why GPUs are pretty applicable to this sort of thing. How much faster is debatable, depending on who you ask. Some people say up to 100 times faster. Other papers have even argued that it's only a factor of like 2 or 3 times as fast. And one thing to note here is that a lot of GPUs are not double precise. They only have floating precision, right? So 32 as opposed to 64 bits or something like that. And so if you only have floating precision, that can actually affect the calculation of your gradient, which affects how you're updating the weights in your network. So as you can imagine, that would have significant impact on your network if you're using floating point. Usually it's overcomable, but if that's a word. But it's good to have the ability to do some kind of double precision computation. So on a more practical note, if you want to train Keras with a GPU, you can pass in the flags here that are before the Python command, which basically say to Theano, I want you to use the first available GPU that you have, and I want you to use with 32-bit precision or floating point precision. And then there's this link here for other ways in which you can use a GPU with Keras. So if you go back through this later, you can access that page to see how. Another point that's worth pointing out is that neural networks require a lot of training data. Because you want to avoid overtraining, the more data that you provide, the more examples that you're giving your network, the more generalizable it's going to be in the long run, right? Because intuitively, it will have seen more examples of the thing you're trying to train it on so that it can perform better outside of your training set. So there's this sort of theoretical bound on how much training data you want, ideally. So in general, you want 10 times as much training data as this thing called the VC dimension of your machine learning model, which basically specifies the complexity of your model. And the problem with neural networks is the complexity of that model is very high. So you need 10 times a very high number of training data to be theoretically safe if you're going to train it. Often in practice, you can't get your hands on that much data anyways, so you just kind of get as much as you can and do the best with what you have. But simpler models are usually better if you have a limited amount of data to play with. So yeah, for an example, the MNIST data set provided with Keras has 60,000 training data. And yes, I did use training data as a plural on there. So now that we've sort of seen how to create a neural network in Keras, how to train it, we're going to look at how to evaluate a deep network in Keras and some other ways. So typically, one of the main things you're going to look at when you're evaluating how your network is doing is the loss function. So the loss function is something that you specify, which calculates the error, how far off you are between each forward pass in your network and your desired result. So if you're saying, to give a concrete example, let's say you put the image of a 2 through your neural network, and it spits out that it thinks it's a 3 with some confidence, and then in second place it thinks it's a 2. You'd want your error function to reflect that it needs to adjust towards thinking it's a 2. And I'm saying error function, which is the same thing as loss function here. So you can record your loss at various points during the training stage and you want to see that loss function is approaching 0. Ideally, you're not going to have any error in your network, right? So here we can see that with the yellow line, for example, a very high learning rate of the optimizer gets a good start on lowering that loss function, but then eventually goes up. And if you saw this graph without the label that said that you had a very high learning rate, you might infer that you had a very high learning rate and it was too high and you needed to adjust it because of the way that your loss function goes way up after getting a good start. So ideally, you want something like your red line there. You want your loss function to gradually go down and sort of plateau at the best value that it's going to get. So that's one way to sort of evaluate your network outside of just looking at the accuracy that you get at the end of it. You sort of want to record its performance at intermediate steps, and that might help you give you some intuition as to how to adjust parameters later on. And that's something that you record during training, and then during validation, you want to record how well each hyperparameter change goes, how well it goes with your neural network and the performance of the network, right? So you can also use validation to record the performance of a couple of different structures of neural network that might be similar or totally different too. But the key here is that you have to have the validation set so that it generalizes well once you're done training. Then there are some tools provided with Keras actually, which help you with evaluation. So these things called callbacks, which record the model state at various points in time. Like we were saying with the loss function, you want to record it at various points during the training, but you can also record other things besides loss, like accuracy. You can go so far as to record the weights of the network at different points and see how they're changing across the layers. Because maybe you have a vanishing gradient problem in your network, right? Where the weights at the beginning of the network are not changing very much because the error isn't making it all the way back through the network during back propagation. There's a tool called NVIDIA Digits. So if you're using a GPU, you can use this with Theano to visualize lots of cool things about your network. It's a pretty cool suite. I recommend checking it out. And then there are visualization packages provided with Keras also, which are pretty nice. So some of the code for evaluating the performance of a model. In the example, if you go on later to the tutorial that I'm referencing from, you'll see this line that says score equals model.evaluate. That's essentially testing your model out on some data it hasn't seen before to see what kind of performance you get. And in the example that's given online, I think we achieve something like 98.5% accuracy on correctly classifying a handwritten digit, which is pretty good. State of the art is higher than that, but for sort of a first stab at a model, that's pretty decent. And then there's also the code in the example takes advantage of those callbacks that I said, which record the model state at various points. So here we access the loss history callback, and we can plot it like so. And we see that our model is in fact learning pretty well. It starts out kind of a higher and quickly decreases to sort of plateau out into a tail, which is what you want, right? That's what you want to see. You want to see your error slowly decreasing without going back up.
So back a couple slides where you had the higher and lower learning rate.
Yes.
So do those also eventually trend towards having a really low learning rate, or do they?
They don't have to. No, there's nothing that says that if you trained for like an infinite amount of time, you would ever get lower. Sometimes, if you're viewing it from the point of view of of optimizing over a function, the learning function for a neural network is not convex, which means that you're not going to have one global minimum that everything's going to converge to eventually, right? You have these local minimums, which are peaks and valleys in your network. And sometimes what happens is you'll get stuck in a bad local minimum, and you won't be able to, your learning algorithm won't be able to go out, right? Because it's constantly trying to go down, but where it is, everywhere is up. So it doesn't know how to get out of the valley. Good question. Any other questions to this point before I go forward? I was up here. Cool. we can talk about some various applications. We're going to wrap up here in a little bit. Besides handwritten digit recognition, deep nets are frequently applied to natural language processing, which is sort of my background with deep learning. So these things called long short-term memory layers are used, which circumvent a traditional limitation of neural networks, of feed-forward neural networks, where each input is treated in isolation. So before, when I mentioned the prediction of the last word in a sentence, you want to be able to remember several of the words that came before, if not the entire sentence, so that you can have a better chance of predicting what the last word is going to be. So that's what long short-term memory layers provide, is the ability to remember previous inputs. And they're really useful and worth reading about if you want to do any sort of natural language processing with deep networks. So here are some links to some examples to fiddle with, written in Keras, written using Keras, written in Python. The top link here is for sentiment analysis. I don't know if any of you are familiar with the sentiment analysis database from IMDb, but basically you try to guess how a person views a movie based on what they wrote about it. So obviously the network's gonna like learn to detect keywords like good and I was happy with this. And it actually achieves some pretty good results. And sentiment analysis is not easy, so it's a good start. And then if you wanted to fiddle around, there's another network here that does some text generation actually. So it sort of will write its own story based on the corpus of a particular author that I don't remember. And that sort of reminds me, there's a not natural language processing related, but somebody recently came out with a network that they fed in different styles of art from different artists in the past. And then they were able to transform images to look like it was painted by that particular person. So things that, everything that they told to look like Van Gogh had made it looked a little bit like Starry Night. It was pretty cool. I forget what that was called, but you can Google that and it's pretty neat. And then that sort of leads into this image recognition. For image recognition using deep nets, traditionally these things called convolutional networks are frequently used. And those networks are good at picking out features of an image and then learning based on those features how to detect things in images. And some examples to fiddle with are listed here. Of course, what we just did was image recognition. We trained a network how to classify different digits of the MNIST data set. And then I cannot remember what this first example is, but the second one is a different digit recognizer. And if we have time, I'll go back and look at what and if people are interested, I'll look at what that second one is. Yeah, but beyond natural language processing and image recognition, there's also tons of other applications for deep nets, and they're pretty exciting. So having access to something like Keras that really lets you quickly get up to speed with deep learning models is pretty nice. And we live in an exciting time, I'd say. This is the link to the examples page of Keras, the official one. And it has lots of really cool examples that you can do. There's one that generates labels for an image just by taking training data that has images with labels as input. So that's pretty neat. And with that, I will take any questions.
So I know the video cards are better for neural for deep learning. Is that a fundamental difference, or is that a library?
It's a tricky question because you're saying, is it fundamentally different than using a CPU?
No, it's fundamentally different from like AMD.
Oh, okay. I think that's mostly a library thing. yeah, AMD cards have similar power and similar capability as far as I know, but NVIDIA has done a really nice job of sort of getting the deep learning community involved, and they have all these accelerator libraries built for NVIDIA, like CUDNN, which is CUDNN, which is especially for deep learning. It has lots of operations that are optimized for the NVIDIA card. And also, for whatever reason, NVIDIA just seems to be doing better at business than AMD currently. So that probably also has something to do with it. But yeah, theoretically, AMD cards, as far as I know, could do about as well as NVIDIA cards.
So it's also similar to AMD CPUs versus Intel CPUs. They are still central processing units, same architecture, but they are slightly different in their implementation. And for some reason, NVIDIA's implementation is a bit better for some applications, but there are other applications that they've shown the AMD GPUs can be just as good. So, it's kind of been this.
Okay, do we have any time?
Yeah, time.
Good. Take a look at how to at actually running these things if we wanted to. Guess we could. First, any more questions? Okay, cool. So yeah, I guess if people want to hang around, I can show some code up and running on my machine. And if not, I think you're free to go, right? Thanks for coming, and I'll move this over. I actually had to download the libraries myself. I didn't have them installed before today, but I used them on a different machine. So the tutorial that I was talking about, I've downloaded it. I think I have to restart Python though. That's not good. I know what I have to do. Great. Well, while that's installing, you can take a look at the tutorial. Yeah, so this is the tutorial on GitHub. It has instructions for how to get Keras up and running with some examples, and also Lasagna, which I've never played with, but supposedly it's also very nice to work with. Both of those are Python libraries built on Theano at the very least. I don't know. So one thing I didn't mention was that Keras can also work with a backend called TensorFlow, which is a Google product that was recently released. So a lot of people are really excited about it just because Google is backing it and they have high hopes for where it's going. Actually, let's take a look at some of the Keras examples because they're pretty neat. Yeah, there we go. This is a network that learns how to give captions to images, and it's built on convolutional layers and also recurrent layers. And then what it does is it merges the two into one network. So basically you have two different parts of the network, one of which is computing a function over the image itself, and then the other part is computing over the input words, the input captions. I don't know, do they have a data set here? Yeah, I don't know if they have the data set pre-imported, but that's a pretty neat one. There you go. Where am I? There we go. Okay. So So this is Keras being trained over the MNIST dataset, and it is using the CPU only right now, because I didn't specify for it to use the GPU. And in fact, I don't have a GPU on this thing. So it'll show the training epochs and the accuracy associated with each epoch. And remember, each epoch is going through all 60,000 images forwards and backwards to calculate some kind of error. So we start off at a sort of high loss, 0.41, and then you can see that it pretty quickly drops to a 0.18. And notice that it specifies the amount of time that it takes for each one of these. So 8 seconds, 9 seconds, 10 seconds. When I run this on my desktop, which has a GPU on it, those are never more than a second. So the GPU is usually much faster for the training part of things. It's worth noting, though, that this model compiled, misspelled, in 0.66 seconds, whereas on if you're using the GPU, it has to go through the NVCC compiler, the CUDA compiler, and that took literally 2 minutes, 120 seconds out of the 150 seconds training on the GPU were spent just compiling the model. So for an easy task like this, the MNIST data set is pretty easy for as far as training speed goes. The overhead of the GPU almost isn't worth it. But then once you get into the more complicated image recognition tasks, like classifying images from the ImageNet database, which has a bunch of images pulled from the web, that'll take, upwards of, I don't know, Pross might have a better estimation of how long that takes.
CPU only?
Yeah, CPU only, what was it, like, 60 days on a CPU, as opposed to 4 days on GPU. So in that case, the overhead of compilation was definitely worth it. Yes?
So what happens once this thing is done training? Like, how do you actually use it to recognize it?
Sure. So you have this model object. So at the very top, it's about to go away, but you'll see I said model comma losses equals run network. So that run network function returns this model object, which contains all of the hidden units, the weights between them, and the activation functions and all of that, everything that you need to do the neural network. And then what you do is you can use this model.evaluate function and pass in your data. that you haven't seen before and that you want to classify now. And it will produce a classification for that data by simply taking the input vector and running it once forward through the network. And then sort of one of the nice things about neural nets is that they set up very well to do multi-class classification. So you're in digit recognition, you're trying to do the numbers 0 through 9, right? So that's multi-class. 0 is a class, 1 is a class, 2 is a class, etc. And I wish I had a visualization for this, but this network is constructed with the output layer, this modeled out at dense 10. That means the last layer in this network is going to be 10 units. And each unit there is going to correspond to 1 digit, right? So when you run it once through the network, how you're going to take the classification, or how you're going to do the classification, is you're going to specify this softmax activation right after that last layer. And that's just going to say, I'm going to take the unit with the biggest value, basically, after I run an example through it. And I'm going to say that that's what the classification corresponds to. So each of those neurons will learn to correspond to a particular digit based on the training data. Let's see if it's done. And it's done. Cool. So that's the loss, and for some reason the accuracy got cut off, but 0.05 loss, and then the accuracy is something like 98.5%. And the loss is computed on the training data, so that's why 1 minus 0.05 is what, 95. So that's the in-sample error, right? That's what you're getting. That's how many of the training data, how much of the training data this network's getting wrong. So actually our test is slightly better than our training data, which means that we did a good job of regularizing this network. We did not overtrain by fitting the input data too much and then losing some accuracy out of sample. Because really all you care about is the out of sample error, right? If we cared about in-sample error, we would just look at the label that corresponded to each training data and get 100% accuracy every time. And our lives would be great, but we'd all be out of a job. Yeah, so that took 244 seconds, which is a little slower than on my other machine. And with a GPU, for this small of an example, it's going to take about the same amount of time. But like we said earlier, using a GPU for much more complex tasks is useful. And then just to show how the example works, we also have this. I think it's called plot losses. Yeah. And that basically uses the fact that we recorded the loss at each batch in training, and then we can plot it later on to see how well our network did as far as learning is concerned. So we did well. We went down to 0.
Is it mislabeling things less than 1% of the time?
Mislabeling things. So that the accuracy for some reason got cut off here. The accuracy, when I ran it earlier, was about 98.5%. So that means that it's mislabeling things about 1.5% of the time. And yeah, we only care about how it does on the test set. We don't care about how it does on the training set, unless you have some strangely high loss value, which would indicate that you did something wrong when you set the network up. So if this graph suddenly started trailing up back towards 1 again, that would be a problem, because you've stopped learning, and in fact, with every update, you're making your network worse. But with this kind of behavior, you don't really care about the loss function anymore. Yeah.
So looking back at that init model function that you have, so where you're doing all of the setup for the model. So where are you getting a lot of those values for how many nodes to add?
Yeah, this is actually a famous network model proposed in the mid 90s, I think, by Jan LeCun for image recognition for this digit data set. So that's where the art of creating these neural networks comes in, as opposed to it being a science, right? You have to pick what the structure of your network is going to look like. And in fact, we can play with some of these values if you guys want and see how it affects the training of the network. So let's say we change this to something like way smaller. Let's say we made this like 250 or something. And then we'll make that like 100. We have to keep that last layer at a 10 because, again, it's a 10 classification problem. Yeah.
So is that number that you added in there, is that changing like the number of nodes in that layer?
Exactly. Yep, it's changing. So that 250 means we went from 500 nodes in the hidden layer to half that. And then we're also doing, instead of 300 in the next layer, we're doing 100. So I'm curious to see how this will work. And then we could fit it with a bunch of parameters if you wanted to try to create some kind of cool.
So put you on the spot real quick. How do you think it will perform now?
Worse.
So how bad?
How much worse?
So you pretty much cut your first 2 layers in half, right?
Right. You'll not see 50% accuracy now, if that's what you mean.
Okay.
It'll probably be, if I were going to put a number on it, I'm going to guess 97.6% accuracy.
So it's going to drop down maybe 1%.
Maybe a percent. Yeah. But so that's kind of an interesting point about deep learning models. Nobody uses the second best model for anything, right? Except experimentation. Everybody, it's sort of like Google versus all those other search engines. Everybody goes for the best. So you have to, that 1% accuracy is huge. That's the difference between you having a job at Google and you being a graduate student in RPI like me.
Is it ever the case when you need to conserve your number of entities in the network?
Yeah, so if you have, especially with deeper networks than this one is only 3 layers deep, but it still, gets the idea across about deep networks. Sometimes going from like a 10 feature input vector to suddenly you're fanning that out to 1,000 nodes in the first layer, it's not always the best idea. Here, the network is actually working by shrinking the size of the network at each layer, which sort of corresponds to getting to the more important features as you move along throughout the network, as opposed to expanding the other way around, which is sometimes a bad idea. And then you're generating more features than you had before and kind of picking things out of thin air and learning what may amount to something meaningless. That's not to say that approach always fails, but that's an example of something that could go wrong. Okay, so I re-imported, and we're gonna watch it train again. We could get a pool going, see who gets closest to the real accuracy. Yeah, what's up?
So that line that says train on 60,000 samples, validate on 10,000, that's the size of the training data versus the test data?
Yes. Yeah, so validate is actually a bad word there. Validate really means test in this case. A validation subset you would typically take it from this 60,000. You probably grab another 10,000, and that you would use that if you wanted to play around with the hyperparameters of the network. So if you wanted to try a bunch of different learning rates for your gradient descent, then you could use the validation set to test each update on, while reserving your test set for later on to test the true accuracy of whatever model you settle on, whatever hyperparameter choices you settle on. And then you can, using that approach, you can still rely on your test data to give you a good indication of how you're going to do on future out of sample tests. So how are we doing? Down to 0.07 lots. The good news is that we're still decreasing. We'll see what this next one is. Okay. Yeah, still decreasing. That's good. Yes, yes.
Is that creating?
Essentially, and each of those nodes corresponds to a value in the vector. So you don't train that for that layer at all. That's always coming by whatever it is. I hope it doesn't cut off the accuracy for this one. Now that I think about it. That'd be good. We can listen to the loss. Yeah.
Yeah, so also just look here for the short, like, it seems like there's not much project related to like the actual test data itself. Or, I understand the last time we said it was a black box process, you don't really know what's going on. But, so is all of the setup for this done in that init model function where we just set up the nodes and say, train on this thing?
Where was I?
Data set?
So you're asking if everything is done in this init model or run network function or something?
Yeah, like what is that? What determines what a good neural network for this particular data set is?
We're not even trying to determine what a good neural network for this data set is right now. We're not doing any kind of optimization on hyperparameters or anything like that, or testing out multiple different variations of it. All we're doing in this code is saying, I constructed a neural network like this. I'm going to train it, and then I'm going to see how it does. So yeah, there's nothing in here that's being particularly clever and trying to tweak it based on how it did. It's just straightforward. Set it up, train it. And yeah, so you can imagine the parameters that we see here, just this, like the numbers and for the dense layers and then the dropout layers, that's